Hi everyone, this quick video lesson is going to introduce you to the idea of a geometric series. We already know about a geometric sequence like this. The first term, in this case a, equals 2, the common ratio is 3. So 2 times 3 is 6, 3 times 6 is 18, 3 times 18 is 54, and so on. Now a geometric series, on the other hand, is when we add each of these terms in a row. So the first term is 2. If we were to add the first term and the second term, 2 plus 6 is 8. If we were to add the first term and the second term and the third term, we'd have 2 plus 6 is 8, 8 plus 18 is 26. If we were to add the first, the second, the third and the fourth term, 2 plus 6 is 8, 8 plus 18 is 26, 26 plus 54 is 80, and so on. Now this is called a geometric series. This is the sum to one term. This is the sum to two terms. This is the sum of the three. We would refer to each of these in turn as S. This one is S, the sum of 4 terms. This one is S3, the sum of 3 terms. S, whoops, that should be an S. S, the sum of 2 terms, S1, the sum of 1 terms, and so on. Now we can keep going as far as we like. And our task today is to try and generate a formula for calculating the sum to any term we like of a geometric series. So let's start with the generalised version. First term is A, second term is A times R. If I wanted to, I could put A times R to the power 1. Third term is AR squared, AR to the fourth, all the way up to AR to the power n minus 1 for the nth term. Now that's my geometric sequence, which we already know. If I wanted to write a formula for the sum to n terms, then I would have to write this with all the additions. A times R plus A times R squared, and so on, up until I get to A times R to the n minus 1. Now, how are we going to simplify this? The trick is to multiply by the number negative R times our sum. Now, what would negative R multiplied by A give? It would give negative A times R. And I'm just going to write it slightly further to the side here. What would AR times negative R give? That would be negative AR squared. What would negative R times AR squared? That would be negative AR cubed. And we would continue along. We would have this one here. This times negative R would be, excuse me, all the way up to we would have an AR to the n minus 1, which would be the previous, and then we would have the last one would be, sorry, that should be negative, A times R to the n, and that's it. That one multiplied by R would be AR to the n. Now if I were to add these two terms, Sn plus negative R times Sn, well, I'd have the A from there, that one plus that one would cancel, that one plus that one would cancel, all the way along to that one plus that one, and I would have minus A times R to the n. Factoring out Sn here, I have 1 minus R. Factoring out A, I have 1 minus R to the power n. And my formula then for the sum to n terms is A 1 minus R to the power n divided by 1 minus R. Now, an alternate version of this formula, if I multiply top and bottom by negative 1, so the negative 1 distributed through the bracket and the negative 1 here, A multiplied by, I could have R to the n minus 1, so that becomes positive, that becomes negative, and then it would be R minus 1. This form is useful if R is a value less than 1. This form is useful if r is a number bigger than 1, but they're both really the same formula. As an example, let's go back to what we had up the top here. We had value of a equals 2. We had a common ratio of 3. And let's go for this last one, where n equaled 4. We were summing 4 terms of this sequence, so this fourth sum should come to 80. And as r is larger than 1, we'll use this formula here. So the sum to 4 terms should be a, which is 2, common ratio, which was 3, to the power of n, which was 4, minus 1, all divided by common ratio, which is 3, minus 1. That's 2 times. Now what's 3 to the power of 4? Well, 3 times 3 is 9, and then times 9 again, that's 81, minus 1, and 3 minus 1 is 2, so the 2's cancel, and I'm left with 81 minus 1, which is 80. So the sum to the fourth term of the geometric series is 80, just as we thought it should be up there. Okay, that's enough for now. Have fun.